Hello students, how are you all? I hope that you are doing well. I am Vikas Monaker, PGT Physics from Kendriya Vidyalaya Lansdowne. Today we are going to study Chapter 9, Ray Optics and Optical Instruments, and this is the lecture number 4. Now let's see that what we are going to study in this lecture and what are the contents of this lecture. In this lecture, we will study about the problem of lens-maker formula. One problem we will take of lens-maker formula in order to understand the concept better. Then we will study the combination of lenses in contact. We will study about refraction through a prism, formula of a refractive index of a prism, dispersion of white light, and scattering of light. So quickly we'll move on to the problem related to lens-maker formula. So the problem is written here. It's given a focal length of a glass lens is given. The power of the lens is asked. It's very simple. Power is the reciprocal of focal length, so you can obtain it. Second part, the radii of curvature of the faces of a double convex lens are 10 cm and 15 cm, and its focal length is given 12 cm, and refractive index of the glass is asked. So it's simple. Then we can apply lens-maker formula 1 upon f equal to mu minus 1 or n minus 1 upon r1 minus 1 upon r2. See, this is a convex lens. It is given double convex lens. So I draw a convex lens for you. This is a convex lens, and if I draw principal axis like this, then this is the first surface and this is the second surface. For the first surface, the center will be lying on the right hand side. For the second surface, the center will be lying on the left hand side. So for the first surface, the radius is taken positive as the center is lying on the right hand side, and for the second surface the center is there on left hand side, so the radius is taken negative. So this has to be considered into account. If the problem is given of concave lens, then accordingly the values plus minus should be taken. Okay, the refractive index of air is taken unity. That means this n is the refractive index of glass with respect to air. If we solve it, then we will get the value of refractive index to be 1.5. The third problem is an interesting one. A convex lens has 20 cm focal length in air. What is the focal length in the water? In the previous video I explained, when the lens is dipped inside a liquid, the focal length changes. Now mathematically we can calculate the value. Initially the glass is there in the air, okay, and we place the value. The focal length is given 20, so 1 upon 20, and then 1.5 minus 1 upon r1 minus 1 upon r2. Now the same glass lens is there in water. So when it is in water, so we will take the refractive index of glass with respect to water. So we'll apply the formula and we will take the relative refractive index. Okay, and then on dividing we can solve and we can get the answer. Okay, so in this way, if a lens is dipped in any solution or in any liquid, its focal length can be calculated. Okay, it will be changed in this case. Okay, and it is also possible that the nature of lens can also be changed. If you have not seen my previous video, please watch it. You will come to know about it. The nature is also change. Okay, it is possible. Now we need to study the combination of thin lenses in contact. If we consider the thin lenses, two thin lenses A and B, here as shown in the figure, A and B, they are thin lenses because there are certain limitations, certain assumptions that we have taken in deriving the formula. Okay, so we need to consider the lenses to be thin so that their optical center is quite close, so we can consider the optical center, okay, of the combination to be coinciding with the optical center of individual lenses. That's why the lenses are to be taken thin. Okay, so this is the first lens A, okay, and this is second lens B. A point object is kept at a distance u. Okay, if the second lens is not there, it will be forming an image at I1 at a distance v1. But since the second lens also exists, it will further converge and the image will be forming at I at a distance v. Here the thin lens are taken, so we are considering all the distance with the common optical center. Now we apply the thin lens formula for both the lenses, and then we try to find out a relation in between the focal length, and we try to consider the combination as a single lens. So first of all, we apply the formula for lens A. The formula is 1 upon f equal to 1 upon v minus 1 upon u. So for the first lens, the focal length is f1. So 1 upon f1 equal to 1 upon v1 minus 1 upon u, as v1 is the image and u is the object distance. Now for the second lens, if we apply the same formula, 1 upon f2, that is 1 upon v for the second lens, v is the image, but for the second lens, the image which is formed by the first lens is acting like an object, so I dash is the object for the second lens. So instead of object, we write object distance as v1. So 1 upon v minus 1 upon v1 equal to 1 upon f2. Now if we see the equations carefully, we can find that the equation 1 consists of 1 upon v1 and equation 2 consists of minus 1 upon v1. If we add these two, 1 upon v1 will be cancelled. So we get 1 upon v minus 1 upon u equal to 1 upon f1 plus 1 upon f2. Since v is the final image for the combination and o is the object for the combination, so 1 upon v minus 1 upon u is written as 1 upon f, where f be the equivalent focal length of the combination. That means if we want to replace these two lenses by a single lens, and it will behave in the same way, and then its focal length will be f. So by this we get the relation 1 upon f equal to 1 upon f1 plus 1 upon f2. That means the reciprocal of the focal length is equal to the sum of reciprocal of individual focal lengths. Or in simple way, if I explain that the power of the combination is the sum of individual power of lenses. Now we need to study the refraction of light through a prism. There you are seeing a prism. It is having these two refracting surfaces. Light incident from the first phase and comes out or emerges from the second phase. This A be the angle of prism. Now you see, if the light incident from the first phase, then it is coming out from the second phase. Then how it is possible? We try to understand with the help of another ray diagram. See, these are the two faces of the prism. Okay, light incidents on face AB, refracts and then comes out from the face AC. If mu is considered as the refractive index of the medium of the prism, material medium of the prism with respect to the surrounding, and if we draw normals N1 and N2, I be the angle of incidence and E be the angle of emergence, R1 and R2 are the angle of refraction for the first phase, and R2 be the angle of incident from the first phase, A be the angle of the prism. Then we can write in this way that in the quadrilateral APOQ, angle A plus angle O, that should be equal to 180 degree. If we draw the incident ray in the forward direction, and the emergent ray in the backward direction, then the angle formed in between them is known as angle of deviation. If you take the triangle OPQ, then you can find out that angle R1 plus O plus R2, the sum of all the angle of a triangle, that should be 180 degree. In triangle DPQ, delta is the exterior angle. There you can see delta is the exterior angle, so it is equal to sum of interior opposite, so that should be equal to this one, I minus R1 plus E minus R2. So if we arrange this from equation number 1 and 2, we can obtain that A equal to R1 plus R2, and instead of R1 plus R2 in equation number 3, we can write A. So we can obtain the relation I plus E equal to A plus delta. That means angle of incidence, sum of angle of incidence and angle of emergence, that is equal to sum of angle of prism plus angle of deviation. So this is an important relation. Okay, with the slight use of mathematics, we can determine this. Now we study the variation of angle of deviation with the angle of incidence. If we plot a relation in between angle of incidence with angle of deviation, then we'll find an interesting result. If we take angle of incidence across x-axis and angle of deviation across y-axis, then we find that initially on increasing the angle of incidence, angle of deviation decreases, and then on reaching a particular value, okay, after that it starts increasing. Further, if you increase angle of incidence, then angle of deviation also starts increasing. So we get a minimum value of angle of deviation, that is called angle of minimum deviation. Therefore, you can see from the graph, when angle of incidence is equal to angle of emergence, then the deviation on y-axis, that is known as delta m, and delta m is called angle of minimum deviation. So in case of minimum deviation, angle of incidence is equal to angle of emergence, and R1, R2, they both are equal. So if we substitute, okay, this in the previous one, then we can obtain an expression for the refractive index for the material of prism. As you can see, A was equal to R1 plus R2. So in case of minimum deviation, R1 is equal to R2. So we can place, so A will be equal to 2R. Then R will be equal to A upon 2. Very similarly, one relation we have got, I plus E equal to A plus delta. If we put I equal to E, that means E equal to I, then we get the value of I, that is A plus delta m whole upon 2. Since light incidence on one face, okay, with the angle of incidence I and angle of refraction R, so we can apply Snell's law. So after applying Snell's law and placing the values under this condition, minimum deviation, we get the value of I a plus delta m upon 2 and R a upon 2. So the formula, which is known as Prism formula, which is there for the refractive index of the material of the prism, that is mu equal to sin a plus delta m upon 2 upon sin a upon 2. That means the refractive index of the material of the prism, that is dependent upon the angle of prism, and it is dependent upon angle of minimum deviation as per the formula. So this is known as the Prism formula. Now we will study an interesting topic which you all have studied in 10th standard, that is dispersion of white light through the prism. Okay, when white light passes through a prism, then what happens? It gets split into its 7 constituent colors. Okay, in the band of violet to red, which you can easily memorize, Vibgyor or Vibgyor, that is violet, indigo, blue, green, yellow, orange and red. So the splitting of white light into the 7 constituent colors is known as dispersion of white light. Now you might be knowing why this is happening. This is happening because white light consists of 7 colors and every color has a definite wavelength, and refractive index is dependent upon wavelength. So the color which is having maximum wavelength, that is a red color, okay, undergoes minimum deviation, and the color which is having the minimum wavelength, I must say violet color, undergoes maximum deviation. So violet is at the bottom and red is at the top, because red has the least deviation and violet has the maximum deviation. So the cause of dispersion is the fact that white light consists of 7 color and every color is having different wavelength, and refractive index depends on wavelength. So the bending for every color is different. Here in the figure you can see that for the red color the angle of deviation is delta R, and for the violet color it is delta V. Okay, one more interesting phenomena that you have studied in class 10th also. Okay, so in class 12th you will study that in detail, that is scattering of light. When light passes through a medium in which the particles are existing, whose size is of the order of wavelength of light, then when light strikes on these particles, it gets deviated in different directions. This phenomena is called scattering of light. Because of the scattering of light, in your classroom, suppose no light source is glowing, still there will be light, because the scattered light comes from windows, comes from door, and that enters. According to Rayleigh law of scattering, the intensity of scattered light is inversely proportional to 4th power of wavelength. That means the color which is having maximum wavelength undergoes minimum scattering. The color which is having minimum wavelength undergoes maximum scattering. Therefore, we can say that red color of light is scattered least and the violet color of light is scattered most. Okay, I hope you know or you got the answer that why the color of the sky is blue. So some daily life examples of scattering of light. Blue color of sky. Sky color is blue because there is a dominance of blue color, because violet band or blue band having maximum scattering. Red color is the sign of danger, or danger signals are made red because it can be seen from distance. Okay, as you can see this laser pointer red also. So this is having, red color is having maximum wavelength, so minimum scattering, so it can be seen from greater distances. Then in the absence of the atmosphere, sky color is black. On the moon, if you see, you have seen the video, then you can find that sky color is black. because there is no atmosphere, so there is no scattering. At sunrise and at sunset, sunrise has to travel maximum distance, so relatively all other colors get scattered. So the dominance of red color is there, which reaches to your retina, so you see the surrounding to be red. An interesting fact, human eye is most sensitive to yellow color. So in this lecture we have studied interesting facts about the nature also, okay, and related to the prism also. So you all must study and take it seriously. Okay, these are very important topics for the board examination. So I hope you have enjoyed. Thank you. Have a nice day.